Thanks for attending the video presentation of our work, Real-Time Neural Left Field on Mobile Devices, which is called MobileR2L. This is the first left field-based model that renders in real time on devices. So in this presentation, I will first talk about the motivations of this work, and also the approaches we take to significantly reduce the inference latency. So my name is Junli. I'm the first author of this paper from Snap. I will first briefly talk about the nerve and its limitations and the recent works on improving the efficiency of nerve. Then it will naturally bring up the motivation of our work, MobileR2L. In 2020, Millenhall proposed the neural rendering work, which is known as NERF. It uses a very simple but powerful way of doing novel view synthesis. It traces arrays and sample points along the array, then it feeds sample coordinates to the network to predict the colors and the densities. Then it will use volumetric rendering to render the RGB values of the pixel. The NERF shows very promising results in rendering high-fidelity images from novel views. Although NERF is such powerful work, the limitations are also obvious. Because of remarching on very densely sampled points and the volumetric rendering, it needs 150 million to 200 million network queries to render one image, which takes about 30 seconds in one V100 GPU. Because of the limitation of NERF, there are many works trying to reduce the latency of neural rendering. For example, the SNERC uses 3D voxel grid to store the predicted colors and the features. And on the other hand, KiloNerf uses a divide-and-conquer strategy to represent part of the scene with a small piece. And the MobileNerf uses meshes as extra information for the rendering. These works successfully reduce the inference latency, but at the cost of storage. The representations such as voxel grid or mesh demand large storage, and it is very hard to scale with complicated scenes or render high-resolution images. The high memory footprint is not desirable for mobile applications as there are restrictions on the RAM usage on mobile devices. Although NERF is such powerful work, the limitations are also very obvious. Because of remarching on very densely sampled points and the volumetric rendering, it needs 150 million to 200 million network queries to render one image, which takes about 30 seconds in one V100 GPU. These limitations motivated us to propose a left field-based approach, which achieves both high speed and low storage, and still maintain high fidelity at the same time. In the left field, rays are mapping to RGBs directly without volumetric rendering. We further leverage the super resolution, which takes low-resolution ray bundles as input and output high-resolution images, which make the model real-time on devices. As for the storage, in our representation, no meshes or grid are required, so the model only needs 15x to 24x less storage compared to MobileNerf. Before going into the details of our work, I will briefly talk about the predecessor work R2L proposed by Wang in 2022, as our work follows the training scheme of this work. In R2L, the author uses left field representations that only need one forward pass during the inference, which reduces the latency significantly. It achieves 30x speed up compared to NERF. Since the left field models the geometry of the scenes in an implicit way, this representation suffers from multi-view inconsistency issue. To resolve this, the author employs a teacher model to distill the pseudodata. They queries the teacher the camera positions and the view directions randomly within the training scene bounds. Then the model is trained on the pseudodata and fine-tuned on the real data to further improve the performance. As a result, R2L shows very promising results in both PSNR and latency on GPU. Although R2L shows good results on GPUs, unfortunately it suffers the large memory footprint issues like other efficient nerf works. It fails to render high-resolution scenes due to bulky memory usage. For example, it runs over 3000 milliseconds on iPhone 12 for 200 by 200 input images. One of the contributions of our work is to enable high-resolution scenes rendering in real time on devices. To achieve that, we propose the model architecture as two major parts, the backbone and upsampling blocks. Backbone consists of one-by-one convolution and multiple res blocks. Note that we are using one-by-one convolution instead of MLP, as we observe about 27% speed up using convolution layers on devices. The backbone serves as the implicit neural representation of the scenes. The upsampling blocks consist of three super resolution modules, which are composed of res blocks and upsampling layers. Because of the upsampling blocks, the model can take low resolution inputs, which reduce latency significantly. For example, we use 8x upsampling and 12x upsampling for both Blender and LFF datasets. As I mentioned earlier, the MobileR2L follows the training scheme of R2L. We also distill the data from the teacher model, and the MobileR2L is trained with the pseudo-data and fine-tuned on the real data. One difference is that we use low-resolution rays as input instead of the full resolution. As I mentioned earlier, the MobileR2L not only achieves high speed, low storage, we also maintain high rendering quality. For the synthetic dataset, we achieve 31.34 PSNR, which beats MobileNerf and Nerf. And for LFF dataset, we achieve 26.15, which is better than MobileNerf. For the storage, our model MobileR2L requires around 15x less storage than MobileNerf on the synthetic dataset. For the forward-facing dataset, our model requires 24x less storage than the MobileNerf. Note that our model requires consistent and low storage for all the scenes, so we don't have risk of out-of-memory error even for complex scenes. We benchmark latency on both iPhone 13 and 14 on both datasets. On average, our model has similar latency as MobileNerf. Our model runs faster on forward-facing datasets, but a little bit slower on the synthetic dataset. In this slide, we're showing the real-time demo for the synthetic dataset such as Lego and Mac running on Snapchat in real time. The left video is taken by another phone and the right one is recorded on Snapchat directly. As we can see, the rendering is very smooth on the devices. Similarly, we are showing the real-time demo on Snapchat for the forward-facing dataset. The MobileR2L can be easily applied to user-taken images because we are not using complicated representations such as meshes. To create your own neural asset, you can take several images using your phone. For the sneaker in this slide, we took about 120 images by iPhone and using CoMap to estimate the poses. Then we can utilize the existing templates such as foot tracking in the Snapchat, and combining with our new rendering, we can create virtual try-on for sneakers shown in the video. And thanks for watching our video presentation of our work MobileR2L.